We often talk about how fast a wave is oscillating rather than how long it takes between each oscillation, and so we often use the word frequency, which is just defined as 1 on the period. So a wavelength would typically be in meters, a period would typically be in seconds, and a frequency would be in per second. And the SI unit for per second is called the hertz. So it's cycles per second. So once you understand these definitions, it's really easy to work out something like the speed of the wave. We know that a given point of the wave travels one wavelength in the period. And that means we know how far it's traveling and we know how long it takes, and therefore we get the speed just by dividing the distance by the time. So if we've got the speed of the wave is equal to the distance, the wavelength is usually written by lambda, divided by the period is usually written by capital T, and because 1 on the period is the frequency, you can also write that as the frequency times lambda. And so you get the speed formula not from memorization. Scientists prefer to understand things than to just memorize lists of equations. You understand that just because you know what the wavelength is and what the period is. Now, as we discussed before, having just one beautiful sine wave is a fairly artificial kind of situation. Even if I sing a really beautiful single note like la, if I were to look at that on an oscilloscope, I would see lots of different frequencies. I'd see not just a sine wave, it'd be a little bit like a sine wave, but it'd have lots of little wiggles on it. And in fact, a real wave is typically lots of these things added together. So you have a particular sine wave added to another sine wave, added to another one, with different amplitudes and different frequencies and different wavelengths and different offsets. And all of that gives you a real wave. But these beautiful sine waves are interesting for some quite simple reasons. If we have very small oscillations in a very wide array of different media, then it turns out that a beautiful sine wave does in fact travel exactly like this at a constant velocity without changing its shape. So it turns out that understanding the properties of sine waves is a pretty good starting point for understanding the behavior of real waves. Going into the detailed reasons behind that is well beyond what we need to do now. Instead, we're going to go on and discuss some more important wave properties.